Good evening, everyone, and welcome to Social Flight Live. I'm Jeff Simon. We have such a fascinating show for you this evening. Don Durston is here from NASA's Ames Research Center to talk about supersonic flight and the X59. I'm so excited for that. Before we get started, just a couple of notes. I have to tell you, there is so many wonderful things happening as fall approaches that I am seeing, especially by checking out socialflight.com and the free SocialFlight mobile apps for Apple and Android devices. And one I want to show you as an example of how there are so many fun things happening out there is this one that I just discovered. Literally, it came in the email and in information happening from my local area. And it's our local Crow Island Air Park pie-in fly-in. And you know, this can only happen in general aviation, right? Where you can find such fun events to go to where you can go there and everybody brings a pie. Go figure. Only again in general aviation. So with that, a couple other things. Our Fly to Win challenge is also happening. Again, it is always in one phase or another. And our current prize we're getting ready to give away is a Lightspeed Zulu 3 headset. Very, very excited about that. So that's a lot of fun. And also our FAA learning system is up. And so be sure to check that out. You can go in and get Wings credits. It'll automatically go to the FAA's Wings system and give you credits. If you're an AMP, that is also available where you can go in there and you will be able to get AMT credits, Aviation Maintenance Technician Program credits, and also as an IA, you can meet your requirement for renewal with 8 hours of education available through SocialFlight's FAA learning system. So be sure to check all of that out. And of course, this program will be available recorded on YouTube and then also on SocialFlight's new podcast. Tonight's broadcast is brought to you by Bose Aviation. You can see us with many Bose headsets that we travel with in a lot of our adventures, and the A20 headset, as well as their commercial headsets. And I will say, a very good friend of mine, Brian Schiff, has just started using the Pro headset from them, and he uses that while he flies for the airlines, and has just been raving. He just started using that headset, and just it's an in-ear headset that's just remarkably good for anyone, especially flying turbine aircraft. So for any of you that are commercial aircraft pilots, be sure to check those out from our partners at Bose Aviation. Now, I'd like to introduce tonight's guest. Don Durston is a pilot and aerospace engineer with over 42 years of experience at NASA's Ames Research Center. His expertise in wind tunnel and supersonic technology are currently focused on the X59 Quiet Supersonic Technology Mission, commonly known as QUESST. The aircraft and the research done by Don and the QUESST team has the potential to revolutionize air travel as we know it, making supersonic air travel over land a reality in the not so distant future. Don recently gave an amazing presentation on the science of supersonic flight and the program at AirVenture 2022. I am thrilled to have him with us tonight. I'm going to bring Don on the line now. Please welcome to Social Flight Live, Don Durston. How are you doing, Don?
Very good. How are you, Jeff?
Thank you so much for being our guest tonight. I'm excited to dig into this. This is extraordinarily cool stuff.
I think so too. That's why I enjoy my work.
So Don, tell us a little bit about your background, because I'm always fascinated by the people that make up general aviation. That's what Social Flight Live is about. And I have to say that with two boys studying mechanical engineering and being fascinated by aerospace, they want to hear your story because they want to know how someone gets into your seat that you have right now, because that seems to be a pretty special place.
Well, tell you what, I'll save this chair for them. So I have to go way back to my very young youth. When I was, 5 years old or so, I looked up in the sky, saw an airplane. I go, I think there's a person in there flying that. And I go, I want to do that. I have to become a pilot. So I knew from that age that I would become a pilot and that that would be a major part of my life for the rest of my life. But of course, it took many years to get to that point. For my 7th birthday, I told my dad, I don't care about presents. I don't want any toys. I just want an airplane ride. So it was so
For your
great.
7th birthday, you said that?
Yeah,
That's,
yeah,
oh my God, that's awesome. I love that.
yeah. Because I had seen them and I had been to the local airports. We lived not far from Fullerton Airport in Southern California. I used to ride my bike there from my house and, you know, sit on the road by final approach and watch the planes. And I told my dad I wanted the ride. So he arranged for a flight instructor to take us up in a Cessna 172. We did a half-hour ride over Disneyland and back. And I've been hooked ever since.
That's awesome. When did you start your flight training?
My first flight lesson was 1978 when I had just become a senior at Cal Poly Pomona in the Aerospace Engineering Department. So I did a little bit then, a little bit more in 79, and then I graduated in 1979. That's when I got the job at NASA. And in fact, just last week, I passed my 43rd year at NASA now. And by the way, this is the only job I've had since graduating from college. So
Wow.
a lot of people are used to switching jobs. I found a job that I like and I'm stuck with it. Anyway, so continued flight lessons. I got about halfway through my training while I was down at Cal Poly. And then I got the job here and I took some time off from flying just to get used to the job and get situated. And then I resumed my training and got my private license in 1981.
Wow. You know, it's close to my heart for people that you know, like my story is the same, where you don't grow up in an aviation family and yet you have that inspiration early on, and usually it's not till, like you said, later on that you finally get your chance to go flying and do it. But it's such a pure experience. That idea, I don't think I've ever heard anything as touching as the idea that at 7 years old, that's what you wanted. I wanted an airplane ride.
Yeah. Well, you know, in high school, they give you all the aptitude tests to help you decide what your career field's going to be. And I just thought, these are a waste of time. I'm going to be a pilot or an engineer. You know, I said, I have to have something to do with airplanes. So I thought about becoming a commercial pilot, but I realized the best way to get the training would be to go into the military and get the hours that way. And in some ways, I have some regrets about not doing that, because my eyesight was perfect until my early 40s. My health has always been good. When I took the flight lessons, you know, my instructor was teaching me about aerodynamics, but I already learned about that at Cal Poly. And I had a real aptitude for it. Flying came easy to me because I just had such a passion for it. And I thought, you know, I could have gone into the military. And the only job that I'd rather have than the one I have right now is to be an astronaut. So, and I did apply through 3 selection cycles back in the, when was that, mid-80s or so. And I found out that I was ranked highly qualified, and I thought, well, that's cool. But of course, there are hundreds of people that are better qualified than me because they have PhD or military time or something. So anyway, so I stuck with aerospace engineering, got this job, and I thought, you know, I can study airplanes for a living, and that would be the, you know, the stimulation of my brain, the stimulation to learn to push myself and apply myself in engineering, and then fly them for fun, which means I could fly them on my own time. I could take up family and friends. So that's been a great combination because I love to take people up for bay tours around the San Francisco Bay Area or trips with my wife or family to Western states. Really enjoyed it.
Oh, that's absolutely wonderful. So it was right out of college, and then you landed here at NASA's Ames Research Center, and that tell us a little bit about the facility and a lot of people have heard the term. It's pretty famous.
Yeah.
Tell us what kind of happens under the roof of Ames Research Center in general.
So I have to give you my first impression of it. So when I was in college, I'd been to different field trips where we went to different companies and saw them. And I actually worked at McDonnell Douglas during the summer of '79 while I was finishing 2 classes at Cal Poly. And so in the companies, there's always the push to, you've got a product and the company has to make a profit. So there's always the push for that. When I came here to Ames, I came up while I was still in school for on-site interviews. And I walked around here and I thought, this looks like a college campus. All the wind tunnels and the buildings and the unique facilities here. And I thought this really appeals to me because it was more of a lab environment, a research environment. And it is Ames Research Center. So that appealed to me. I think at the height we had, it was over 30 wind tunnels here. Very few of them are out anymore. But yeah, starting in the 50s, or even, well, the big wind tunnels, I think, was started in 1939 or 40 by 80 foot wind tunnel. And then they've added on to an 80 by 120 foot wind tunnel here, which is the largest wind tunnel in the world. We have various subsonic, transonic, and supersonic wind tunnels. The sonic referring to the speed of sound, which at sea level is 760 miles an hour. So if I say supersonic, that's air moving faster than the speed of sound. So our workhorse tunnels are the 11-foot transonic wind tunnel, Mach 0.4 to 1.4. So the Mach number is just that number times the speed of sound to get the speed. And we have a 9x7 supersonic wind tunnel that goes up to Mach 2.5, and I've done a lot of sonic boom testing in that tunnel. We used to have a 3.5-foot hypersonic tunnel that would go to Mach 10. So that was used for a lot of its lifting body shapes. And another spacecraft that would re-enter the atmosphere. We've got arc jets where they do heat shield development. Most of the heat shield development within NASA has happened here, where they have, it's not necessarily the high speed of the flow, but it's the high enthalpy. Enthalpy being kind of a measure of the temperature or the temperature gradients, the temperature, heat transfer that happens for a body that's in a flow like re-entry. When the shuttle re-entered the atmosphere, its initial Mach number at the top of the atmosphere is Mach 25. That's screaming fast.
A lot of friction.
A lot of friction. So I just love seeing all the facilities here. And when I started my work here, I had my things to do to work some wind tunnel tests, but my mentor said, just feel free to take some time, walk around, look at the facilities and talk to people and find out what this place is all about. And I loved that freedom here.
That's amazing. That is so, so cool. So let's start, we have such limited time to understand a subject that you've spent your whole career on, and that is so broad. So we'll try to boil down what we can. But
yeah, sure.
Let's start with some basics on the whole concept or the history of supersonic flight, because I think two things. One, I think a lot of people may not totally understand what it means in some ways. And then the other one is when we think about it, right, it all started when we think about the X1, for example,
yep.
and what that meant.
Chuck Yeager. Yeah. So do you want me to give you kind of a brief verbal history on that?
Please, just a little bit of an overview here, and I'll show that one because it's one of my favorites.
There it is, the X1. Beautiful airplane. So, and I believe that's on a pedestal at Edwards Air Force Base for those who want to make a trip there and see it. So that reached supersonic speeds by brute force. It had the rocket engines in the back, and they needed that extra thrust because they didn't know how to design an airplane for low drag at supersonic speeds. So it's kind of a bullet shape, kind of fat, and the wings are not swept. Not ideal for supersonic flight, but they did it. And Chuck Yeager produced the first sonic boom in 1947. So that was the first supersonic flight. Others flew other NASA and Air Force test aircraft after that. Think of Scott Crossfield. I think he was the one for the Douglas D-558 Sky Raider. That was the first plane to break Mach 2. That was, I think, in the early 50s or so. And then they eventually built more and more planes that could go faster and faster. There was another plane that broke Mach 3 for the first time. And so NASA and the Air Force were just having fun, making all kinds of new planes, went very fast. And to me, the most exciting one was the X-15. I think
Oh
it's Mach.
God, that used to be my favorite. I remember doing a model of that, and Estes even made a little rocket like version to of that thing. That the
Good.
X-15 was so cool.
Yeah, yeah. I think it was Mach 6.7 or something, and it was essentially out of the atmosphere.
So help
So
us understand the basics. What does it mean when we talk about the speed of sound, and what is the significance of that why is that govern speed for those of us that don't fly using, knots in a general aviation aircraft?
yeah, yeah, right, right. You have to think about, my voice is going to the microphone on my computer at the speed of sound. So the speed of sound is the speed at which pressure waves move through the atmosphere or move through any kind of medium. The speed of sound is different in water because it's much more dense. So when you think about an airplane flying by, if it's going well less than the speed of sound, then you hear it from some distance away, and it's coming toward you, and you hear it. And then as it gets closer to you or right even with you, then you're hearing the loud sound from it. If it's going close to the speed of sound, like if you're at an air show and you see it coming in the distance, you see it, but you don't hear it. But if it's a little bit below the speed of sound, then it's getting closer to you, and you're starting to hear the roar of the jet engines and the airframe noise and all that. And then when it gets even with you, it's very loud. If it's going Mach 1 or Mach 0.99, there we go, that's a great illustration. Okay, so the chart shows F-18s in 3 different positions. One when it's going subsonic, one when it's going Mach 1, right at the speed of sound, and the other when it's going supersonic. Okay, when it's subsonic, the pressure waves or the sound coming from the airplane are going ahead of it, but they're also going behind it. And in the chart, it shows the pressure waves ahead of it being compressed, and that's because the airplane is moving. The pressure waves behind it are kind of stretched out. So it doesn't mean that the pressure waves go out at different speeds in different directions. All it means is that the aircraft has moved away from the center of the largest circle there and has moved forward a bit. And so, the pressure waves out in front of it are not getting as far ahead of the airplane as they would if the airplane was just sitting on the ground, not moving, but with the engine running, and you would hear that. Or just like if I do a clap, then the sound goes out in all directions evenly. Okay. So if the airplane is going,
kind of like what we're used to out of trains and like a Doppler effect concept at that point.
yeah, exactly. In fact, that left-hand chart there is a good illustration of the Doppler effect, because when a train's coming, you hear it going, there's a reduction in the pitch of the sound. I'm not a good singer, so I shouldn't do those kind of things. But the gaps between the pressure waves in the left side of the chart are an illustration of that. So thanks for bringing that up. When you're going Mach 1, now the sound is not able to get ahead of the airplane at all. It's staying right even with the airplane. And in fact, right where the arrow under the word overlapping is pointing, that's right at the tip of the nose. And you could draw a vertical line right there. That line is essentially the line of the tangents of all those circles that have built up from the sound coming from the airplane, but the airplane nose happens to be right at that tangent. Tangent just being where the circles kind of meet it like that. So if you're at an air show and the plane's going Mach 1, it'll be flying along, you won't hear a thing. You could whisper to your neighbor and they will hear everything you're saying until the plane gets right even with you, and then boom, you hear the very loud sound all at once. It's all those pressure waves reaching you at the same time, and then of course it's just the sound just carries on as the plane goes by. If it's supersonic, then each of those circles on the right-hand side of the picture, the small ones are right at the nose, the bigger ones are behind it, and that's because the sound is not getting ahead of the airplane, it's falling behind it. And so those two lines at the slant angles there, those are the tangents of all those circles. If you draw all those circles and just draw a line along all those circles, that essentially is the shock cone or the shock waves from the airplane.
Got it.
So if you're in, well, fighters are not allowed to go beyond Mach 1 at U.S. air shows. but if you grew up in the 60s like I did, fighters were passing overhead all the time, making sonic booms. That's one thing that got me more excited about airplanes. I was hearing F-4 Phantoms and F-104s flying overhead, making sonic booms. And I said, Dad, I want to do that. So anyway,
so is that true, by the way? Like I didn't know that even at air shows, there's never a waiver. They don't actually go past the speed of sound in those cases.
Yeah, I think that's generally true. There may be some exceptions. And at Edwards Air Force Base in Southern California, where NASA Armstrong is, they have a supersonic corridor there. And it may be that in some air shows, maybe they do demonstrate, a sonic boom.
So help me understand this. One of the most enlightening things I've learned from you over time has been that we talk about this idea of a sonic boom, which is our perception only at the ground.
Yeah.
It's not, explain that, because it's not really, quote, a boom in reality.
Yeah, thanks for bringing that up. So the press gets this wrong quite a bit, and it just really makes me mad when I see them do this. So, and I've had people at public events say, why don't you just make a supersonic airplane that will take off, fly out over the ocean, accelerate supersonic speeds, make the sonic boom, and then fly across the rest of the country without the boom. Okay, that's not how it works, folks. The sonic boom is continuous, and the best way to explain it is that it's like a boat. Okay, if you're on a boat traveling through the water, if you're going slow, you can see the waves lapping up in front of the boat. If you're going fast, you see the waves kind of come out from the bow of the boat in a V shape. And you look back and you can see the wake and the waves going out in a V shape. That's analogous to supersonic flight through the air. So just as a boat driving by on a lake will pass people on the shore, one person on the shore will see the waves lap up on the shore when the boat hasn't even passed. The next person is maybe a few hundred feet further down the shoreline. But in a few seconds, the boat will be there, and that person will see the waves. So a boat can drive all the way around a lake all day long, and everybody along the shore will see the waves come up on the shore. So same thing with a supersonic airplane. If a supersonic airplane is flying from New York to LA, everybody in between will hear the sonic boom because the pressure waves from that pass over the land for all the time that the airplane is going supersonic.
Right, it's just passing over. I think one of the reasons perhaps that this can become so confusing is it gets mixed up with this idea from history of passing the sound barrier.
Yeah.
That the idea of going faster than that is some barrier you burst through, and that's the same thing as the sonic boom. Tell me a little bit about the idea of getting through this idea of a sound barrier and what it means to the aircraft that you work on designing.
Yeah. So first of all, there is no sound barrier per se. Okay, the barrier, the difficulty in going supersonic is the drag. So the drag increases a lot when you're going transonic. That is, you're somewhere below Mach 1 and maybe just a little bit past Mach 1. You got shock waves that will build up on the airframe, over the wings, over the canopy, and stuff like that. As those shock waves develop, that creates more drag in the airplane. The drag is the resistance of on the plane, imparted by the air passing over it. And so you overcome the drag with the thrust, of course. So the barrier really is overcoming the drag. And Chuck Yeager in the X1, he did it with brute force. He had 4 little rocket motors in the back of that X1. It's a very high drag vehicle, but he had lots of thrust. So the barrier was just overcoming the drag, but the drag for any airplane is much higher when you're going supersonic than subsonic. There's actually a plot, and I won't get into it, but it shows that drag increases dramatically as you go through the transonic range and into the supersonic speeds. So you still need a lot of thrust to continue to go supersonic. But if you can overcome the drag, then you've beaten the sound barrier. You've broken the sound barrier.
Do you think that some of this kind of comes from like the really old school thinking of science before they got to that point, that when people thought perhaps there would be a barrier to doing that?
Yeah, I think so. You know, it's hard to imagine that they actually thought that there was some kind of barrier in the sky, because the sky is just full of air. If you're not moving through it, the air is, you know, aside from wind or hurricanes, you know, the air is just there. But people thought that, gee, there's some kind of barrier and it's going to rip the airplane apart when you pass through it. So
yeah,
they were right in the sense that if you don't design your airplane carefully and take into account the changes in the pressure distribution, the variation in pressure over the wings and the tails and everything on the plane, those pressures shift as you go from subsonic to transonic to supersonic. And what we call a center of pressure, that is, think about all the pressure over an airfoil, whereas the center of that pressure acting, that center of pressure moves aft when you go supersonic. And if your tail, like the planes that you and I fly, you know, they have a horizontal tail and use that for pitch control. But if you go supersonic, that can actually put so much pressure on the elevator or an all-moving stabilator on, like on a fighter airplane, that can put so much pressure on it that you may not have enough force. You may not be able to impart enough force in the control stick to pitch up or down when you've got that difference in pressure built up there. So that was one of the barriers, I think. They thought about, can you control an airplane when it's supersonic? And certainly the early supersonic airplanes had control, they had stability control issues. Then they began to understand them, and then they were able to design them so that you can manipulate the control surfaces despite those pressure changes. I hope that
makes
helps.
a lot of sense.
Too much.
That makes a lot of sense, I think, and the graph, of course, or the chart that, you know, showing how that speed, you know, how those pressure waves affect things, that kind of, I think, makes more sense as to why you have to design differently in a different regime. The other term you mentioned, which we see in the news for you know, military reasons and other things, is this concept of hypersonic. How does that change or relate? You kind of explained why supersonic is a line in the sand to some degree for design.
Yeah.
What does hypersonic mean?
Well, hypersonic is just, you know, it's like hyper anything. It's to the extreme. So supersonic at the extreme. I'm not sure what the official definition of hypersonic is. I think some people consider it, you know, as low as Mach 3 or Mach 4 or so. Generally, you know, you think of like the Mach 5 to Mach 10 range. And companies have been doing research on different vehicles trying to learn about hypersonic flight. You can look back at various X-planes. There was the X-43. There's a hypersonic flight demonstrator. So in hypersonic flight, you know, you think of that chart that you showed, that showed the shock waves coming off the F-18 at an angle about like this. That angle might correspond to about maybe Mach 1.5 or so. But in hypersonic flight, if you're up above Mach 3 or Mach 4 or whatever, you can't even speak of the shockwave angle, because those shock waves are just at such a small angle to the airframe, they're just trailing way back. So it's really a different flight regime. The first problem is heating. You know, you're running into a lot more air molecules by going very fast like that. And so that produces heating on the airframe. You know, the X-15 went above Mach 6. It had extreme heating. Even though it flew very high, and there are very few air molecules up there, it still experienced a lot of heating. The SR-71 had to be made of titanium for the most part because of the extreme heating all over the airframe, not just in the engines. So Then the chemistry of the air and the interaction with the airframe and the engine is totally different. So you really have to get into the different processes and the thermodynamics and the chemistry of the air when you're at hypersonic speed. So it really is a different animal than just supersonic flight.
So it sounds like it's very different, but at the same time, it's also maybe a little bit gray compared to a very definitive line in the sand of supersonic.
That's fair.
Let's get back to the supersonic. I want to show another really cool image you sent. And just tell me what we're looking at here.
Okay. So this image is like the one, if you can see that I'm pointing at the picture in the conference room here of the two T-38s from Edwards Air Force Base, Southern California. They are going a little bit above Mach 1. I think the Mach number in both the picture that you're showing and the one on the wall behind me, I think the Mach number is around 1.05 or so. So it's not, high supersonic, it's just low supersonic. But what it is it's one of my coworkers who works 3 doors down from me here in my building. He's like a technical professional photographer, technical imaging methods. So he rode in the NASA King Air, a twin turboprop airplane that had a camera port in the bottom of the plane. Okay, so the King Air was flying, let's say, at about 30,000 feet at its normal cruise speed, a few hundred knots. And they set up the flight in advance so that the T-38s would fly in formation under the King Air, like maybe 5,000 feet below, at some given Mach number. And then my coworker, JT Honig, was snapping pictures as the T-38s, he'd take some pictures before the T-38s got within the camera view and continued taking many pictures, probably more than 100 pictures that make up this one picture here. So he took pictures of them as they passed by. And then when they were done, they stopped taking the pictures. Then you think about at Edwards Air Force Base, it's over the desert. So you've got a lot of sagebrush, Joshua trees, a lot of variegated landscape underneath. So each individual picture shows the two T-38s and all the landscape underneath. But if you are looking at a computer monitor and just flash those pictures one at a time on the screen, you can start to see some clear distortions of the landscape underneath, and that's because of these shock waves. Okay, the shock waves, just like in the other picture you showed, is kind of the buildup of the sound waves, and so the shock wave is an abrupt pressure difference. So that the dark blue areas, like from the nose around the airframe, that's a shock wave because the air is being pushed around the nose. If you think about the nose of a fighter airplane like this, the air is coming along, and then the air has to turn to get around it. And so it's turning, in all directions around the airplane. So when that turns, the air is kind of bunching up there. And if you're going supersonic, then that creates a shock wave, just like in the other illustration with the F-18s and the circles that, are trailing off from it.
That makes a lot of sense. There's one here that actually shows that a little bit, and you kind of explained it's similar to what you might see with a heat coming off of a road or something else. It's a distortion.
Yeah, it's a distortion. Heat from a road or from a train smokestack or something will distort the image of things in the background. And this is one of the Blue Angels flying at Fleet Week in San Francisco. I didn't take this, I wish I did, but if you look closely, you can see that there's a little shock wave just above the canopy behind the pilot's head, and that's distorting the view of the trees and the ground in the background there. Then you look back further behind on the aircraft, you can see there are a couple of antennae on the center of the fuselage, and from there up to the vertical tail, there's some curved shock waves that you can see just barely. And then as you look above the vertical tail, you can see there's some shock waves at a slight angle and other shock waves that are near vertical just behind the vertical tail. And you can even see the distortion caused by the shock waves in the sky just above the top view of the land there. So, and of course, shock waves coming down from the airplane too that are churning up the water, just like a boat wake. But here you have an airplane wake, but the airplane's not touching the water. And that's
Right.
just because you got an abrupt pressure difference there. So
It's really amazing. And so you have camera systems that you use at Ames Research Center that actually measure this, that help you with your designs.
yeah, yeah. The cameras, they're nothing too fancy. I mean, yeah, they're very expensive, but you know, they're very high speed and they're very high resolution cameras. But you know, anybody can buy those. But to make those pictures and to get those shock waves, you know, he takes a series of pictures and then through a process of kind of combining all the pictures together and eliminating the background, then all you see are the distortions in the flow. And that's how you get this picture like the one behind me and the one you just showed. It's an amazing process. So
And is that the air boss process?
yeah, that's AirBoss. We call it air-to-air background oriented Schlieren. So it's AIRBOS. And Schlieren is just a German word that means streak or like streak line or something. So, but we toss that word around here like it's, you know, everyday language. And so we call it background oriented Schlieren because you're using the desert background underneath the airplanes in order to get a variegated background so that you can see the distortion of the background caused by the shock waves.
Wow.
That's
So
about it.
so let's talk for a sec. Is this is the goal. This is what you guys are building right now
Yes,
or in the process on.
yes.
Tell us about the QUESST mission and the X59.
Gladly. That's the thing I like talking about the most. So the QUESST mission, it's QUESST, Q-U-E-S-S-T, the extra S is for supersonic. So it is NASA's quest to enable future commercial supersonic flight. That is our mission. So we have funded Lockheed Martin in Palmdale, Southern California, to design and build an airplane designated the X59 by NASA. We want them to design and build this airplane that will have a quiet sonic boom. No other airplane in the world has ever been made and flown that has a quiet sonic boom. They're all loud sonic booms. The Concorde boom was between 100 and 110 decibels, depending on where you were relative to it. Fighter airplanes are all around that range. We're hoping that the sound level from this airplane, that the sonic boom loudness will be more like about 75 decibels. And we're hoping it'll be more like a sonic thump, like a thump thump sound instead of the loud boom boom, you know, that is so startling and you can feel the pressure waves. So Lockheed started designing this airplane, I think it was as early as 2016 or 2017. And then I think they started fabrication of it in 2019. And the airplane is nearly done now. Okay, that's a wind tunnel test that was done in the Langley 14 by 22 foot subsonic wind tunnel. So that's not a supersonic test. That model is about 15 feet long, and they were looking at the low speed aerodynamics of it and the ground characteristics, you know, when it's down close to the ground. But the X59, the airplane is nearly built now at Lockheed Palmdale. The rollout will be over the next few months. First flight is scheduled to be, well, it's hoped that it will be early next year, sometime in the first few months of next year. I can't say exactly when. It'll fly when it's ready. They're working hard on it, but that'll be exciting to see it fly for the first time. And I would love to be there when it goes supersonic so I can hear the sonic thump, hear how quiet it is to a normal boom.
So what's different? What is it about the work that you are doing and all the others are doing as part of the QUESST mission that's going to create an aircraft that we can whose science or technology can translate into commercial supersonic flight that people will tolerate? What really is different about it?
Yeah, yeah. Well, we're talking about the differences. How about if I show you my display model here?
Oh, then let me turn this sharing off there, because
There
that's
we
the
go.
best model around.
Yeah, this is a beautiful little model. Actually, you can buy these models from NASA. So this is about a 20-inch long model. You can see that the first thing that you notice about this is that the nose is very long. The airplane is just barely under 100 feet long altogether, so it's about a third of a football field. But the nose itself is 38 feet long. No other airplane has been made with such a long nose. I remember the Douglas X-3 Stiletto had a very long nose, but I'm not sure it was this long compared to the length of the rest of the airframe. So I talked about how when a plane is flying through the air has to get out of the way as the nose comes in. So the air is being pushed out of the way. If the nose is very, very sharp, you can see this really comes to a point here, then the deflection of the air is not very much. And so the initial shock wave from the nose is much weaker than it is from, say, you think of modern fighter aircraft, an F-18 or an F-15, F-35. They have sharp noses, but the angle of closure on the nose is much more steep than this. It's a very shallow angle here. So that's one thing that really makes a difference for the X-59. You also notice that there's no canopy bump. All the modern fighters, they've got a canopy that sticks up. Well, anytime you deflect the air and push it out of the way, you're creating shock waves. So if you had a big canopy bump there, the shock waves would go up from that, they would go out to the sides. And just like how sound waves, like when I'm talking, they go out in all directions and bounce off things, shock waves, even from the upper surface of the airplane, will find their way down below the airframe and go down to the ground. So a canopy bump would have created a louder sonic boom for this airplane. So there's no canopy bump. The aft canopy for the X-59 is literally scavenged off of the rear canopy from a T-38. So some poor T-38 that's beyond its life, it sacrificed its canopy. Then you can see there's a small window just forward of the canopy. That's a little side window for the pilot to look out the side. But the pilot has no forward visibility. So this is a camera bump right here. If you can see this little bump right in front of the canopy. So there's a camera there. And so the camera is looking along the nose, and the pilot will have a large screen in front of him for the out the window view, in addition to seeing, the PFD and the MFD, the primary flight display, a computer screen with all the flight information on there, and the multifunction display for other aircraft parameters. So the wings are highly swept back. That also helps reduce the sonic boom a bit. And it has canards and the T-tail and the stabilators. All the shock waves from those will tend to merge as they go down towards the ground. And it's really the computer optimizers that take the initial design from the designer, and then they optimize the placement of all these control surfaces here and the shock waves from those. And you're really trying to optimize how those shock waves will merge as they get down toward the ground. And if the initial shocks up front are weak, then instead of a loud, abrupt pressure change, which causes the first of the two booms, you want the shock wave to be kind of a gradual slope there instead of just a straight up shock wave. When that shock wave passes your ear, then you hear that as a loud boom. So we're hoping that it would be more like a sine wave shape to the ground pressures signature, the distribution of pressures in the ground. So that.
Could you say again what your target is as to what it would sound like when this aircraft flies over land supersonic as it is designed to do over populated areas?
Yeah. We're hoping that it'll be down around 75 decibels. So if you're in a restaurant and the restaurant is moderately crowded and there are normal conversations going on, people all around you, that's probably in the low 70s, maybe up to 75 decibels or 78 if somebody's a little bit louder. So we're hoping that whether people are outside or inside of a building, that there'll be this kind of thump sound, maybe like distant rolling thunder, but not such a sound that's so abrupt and intrusive, but more like a thump sound. And we want the sound to come on gradually. So 75 decibels, that's probably equivalent to your neighbor, slamming his car door, in front of his house. So 20, 30 feet away or whatever. So we're hoping that it'll be down below that level, and we'll see when it flies.
And the advantage, of course, is that we're flying today in commercial airliners always well below 600 knots, 600 miles per hour, I believe. And this has the potential to dramatically change our flight times. Is that right?
Yeah, it does. It does. So this airplane is just a flight demonstrator, that is to demonstrate the technology for it. But, it'll just hold one single pilot. And you would never scale this airplane up and make it a passenger airplane. You have to start with a new design. But the aerospace companies can design future supersonic airliners using the design principles that we applied to this airplane. So, long skinny nose, wings swept back, tailoring of the shock waves from multiple surfaces. So they will apply those principles, and then they can design an airplane that can hold many people. And hopefully, the X59 is planned to fly at a cruise Mach number of 1.4. We're going to take it over various cities around the US and get the public's reaction to what we hope is a sonic thump. And so it'll fly at Mach 1.4, 55,000 feet. Future airliners, we're hoping that they would be gradually increasing in speed as we learn more about how to make them quiet. So maybe they'll fly at Mach 1.6, 1.8, and we hope to cut travel time for cross country or even long distance flights over water. Hope to cut travel time in half. Everybody would like that.
Yeah. So it sounds as if there is both advances in technology as well as this tour that's coming to a lot of metropolitan areas where we will all get to see this or hear this, not see from 55,000 feet, but hear for ourselves at least, as it goes by and make a judgment call on it. There's also regulatory changes that you're hoping to usher in by being successful with this program.
Absolutely. Yeah, that's the main goal of the program, is to take this airplane, fly it around different communities around the US, and that'll be starting in 2024, probably continuing for at least a year and a half or so. We haven't selected the particular communities yet, but so we want to take measurements in the air of the shock waves. We want to take measurements using microphones in the ground to look at the pressure distribution and what the actual sonic boom in the ground is like. And we want to get people's reaction to it. We want them to hear it and to tell us, did you find that annoying? Did you hear it at all? What do you think of that? So we are going to be collecting a very large data package over a couple year time frame. And we want to present that package to the FAA, the Federal Aviation Administration, and to ICAO. The pilots who are watching this are familiar with that, the International Civil Aviation Organization. It's kind of the governing body for the international community, not just the FAA. So we want to present that whole data package to them and say, we've applied these design principles in the X59. So if future airplanes can be designed by companies with these same design principles to have a boom that's quiet as the X59s, then we want the FAA and ICAO to rewrite the rules and say, okay, supersonic flight over land is permitted if you can demonstrate that your sonic boom will be less than some decibel level. That's our goal.
Which wouldn't that have been wonderful if that were the way it was written to begin with, right? Like if there's a problem, the regulation should address the problem, not the symptom at the time of being, of going fast. Right now we say you're not allowed to go supersonic, but really it should just be you can't exceed this decibel level in this circumstance, and then go at it. Design anything you want as long as you don't disrupt people
Yeah.
in this way.
Yeah, yeah, exactly. But back in 1973, when the FAA instituted the ban, you know, they and we had no idea how to design the airplane for a quiet boom. So they just said no supersonic flight over populated areas.
Right. Of course, the Concorde was loud, which was the only aircraft, at least here in the United States, flying, and in Europe,
Yeah,
I lived near Dulles, and I can say even when it wasn't supersonic, that was a very loud plane.
it was. It was. Yeah, those four turbojet engines, they're just extremely loud. I've never heard it
It
myself,
was
but I
cool
watched
though.
it. Yeah. So in addition to studying the sonic boom problem, we have to address the takeoff and landing noise problem because any supersonic airplane is loud. We have to address, the emissions. It's going to be flying at high altitude, and there will be a lot of emissions at high altitude. We're addressing that. Airframe efficiency in terms of lift to drag ratio, things like that, and propulsive efficiency. How to make jet engines more efficient in general and burn more cleanly. We have all these different aspects of our commercial supersonics technology project that are addressing these different technology areas. But the sonic boom is the main barrier that we're facing right now.
Right. I would imagine that heating of the structure and things like that, like we always have heard about with the things like the SR-71, must be an issue as well.
Well, when you're below Mach 2, it's really not an issue at all. And I've heard from some of the fighter airplane pilots that if you're up around Mach 2.5 or a little bit above that, then heating can be an issue. And they may be limited in the amount of time that they can go that fast if they don't have the right materials in the airplane that can tolerate the heat.
Okay, so that's not the issue. It's just going to be the other things you've talked about noise, and efficiency.
Yeah. Below Mach 2, it really won't be much of an issue. If you're flying at Mach 2 all day long, you will have some airframe heating, and you probably need to design for that. I won't say it won't be an issue at all there. But Mach 1.4 for the X59, that's really not an issue.
Now, I'm pretty sure you're hiding something else there you can show us from the wind tunnel.
I am. So, yeah. So I was thinking I'd say this right at the beginning of this talk, but my role, my title is aerospace engineer. My title on the project, on the Supersonics project, is Sonic Boom Wind Tunnel Testing Lead. So I've done wind tunnel testing throughout my career. I think I've been involved with or been in charge of 46 different wind tunnel tests in various NASA wind tunnels. But lately, since 2008, I've been running sonic boom wind tunnel tests, mostly in our tunnels here at Ames, and I've gone to NASA Glenn Research Center in Cleveland, Ohio, to run sonic boom tests there too. So the most recent sonic boom tests that we've done have been with this model. This is my favorite model of all. This is the X59 model. It's a 1.6% scale model of the X59. You can see it's very similar in size to the plastic display model, but a wee bit more expensive. I'm not going to say how much, but
no.
But this model, it's beautiful. We have run this in the Glenn 8x6 wind tunnel. It speeds up to Mach 1, almost 1.5. And we have also sent this model to Japan, to JAXA, the Japanese Aerospace Exploration Agency. They ran it in their tunnels at about Mach 1.4. So it's an amazing model. We have different wing surfaces with flaps and ailerons that can be at different angles. The stabilator here, I can take off these stabilators, which are like the horizontal tails of primary control surface, and put on ones at different angles. We have different angles of the T-tail, so I can remove that and put on a different one. The canards for the X59 are fixed. Lockheed determined that the canards at this +5 degree angle are just fine the way they are. They help with the lift and also the shockwave tailoring. So this is a beautiful model. Some of the tolerances, like how the wing fits together here at this wing joint and with the fuselage, the tolerances have to be less than 1,000th of an inch. So it was quite an effort to build this model and to make it accurately. but they did a great job. So
I
it
had
was
no
just,
idea that was modular. That's fascinating.
yeah, yeah. In fact, you could see that in the center section here, I mean, the canopy is over this part, but the center section, you can see it, you might be able to see there's a different color of the metal there. This piece is aluminum, the rest of it is high strength steel. This aluminum piece can be removed, and we actually can mount it in the wind tunnel with what we call a blade strut, a piece of metal, you know, with kind of a sharp leading and trailing edge, a little curved shape around it that attaches to the model here, and it holds it in the wind tunnel like this. The reason that you want to hold it here is so that you don't distort anything in the back end. And so as we have a device in the wind tunnel that can measure the pressures in the flow field below the model. Okay, so we're looking at the shock waves coming off of all these surfaces. So we can mount it with the blade strut and measure the pressures from all these different surfaces this way. But we can also put what we call a sting, basically a cylindrical steel rod that would go in at this location, and it actually kind of replace some of the structure here, but maintain the shape in order to hold it from the rear. And then we left this filler piece in place here so that we will not be distorting the forward part of the model. So we tested it both ways, and we're looking at the pressure distribution below the model from that. So
Wow.
this is
Well, that is
latest.
absolutely gorgeous. What a beautiful, piece of art and science rolled into one.
Yeah, it is. There are plenty of websites that show pictures of this model in the wind tunnel, so I invite the audience to go to the nasa.gov/QUESST, QUESST website, and you can find pictures of this model in the various wind tunnels, as well as other models that we tested in the Supersonics project.
And that's a very important thing I want to point out as we come close to the top of the hour here, is that everything is at nasa.gov/QUEST, which again, QUESST. There's a lot of amazing things there. You could even print out a 3D model of the X59. We're already playing with, we're experimenting with that here.
Right.
They've got models. There's a version you said that people have created for, did you say X-plane?
Yeah, so a few years ago, prior to the pandemic, we had student interns at NASA Ames here, NASA Langley in Virginia, NASA Armstrong in Southern California. They use the X-plane, it's the commercial software that you can buy for your laptop to run a flight simulation. So they got the geometry for the X59, but they had to develop the aerodynamic model, the propulsion model, the stability control, all this stuff. And so the three students from the three different centers made flight simulation models that you can run in X-plane. I got that model here on this laptop, and I played with it. So if you hunt around on the NASA websites, you can find the link for that, where anybody can download those flight simulation models.
So you can make a 3D model for yourself, get pictures that are out there, fly it on X-plane, and most of all, keep your eye on the news in order to see when the X59 is going to be flying early next year, and then making the tour at some point over all these major cities and getting data points where we can all vote, yes, we do want this in our future.
Yes,
and look for changes.
Yeah, indeed. So there are many other people on the project that are probably better qualified than me to speak about the X59, but I'm one of them. There are many people doing this whole thing, and hats off to them for such a great project and making such a great airplane.
Absolutely. And Don, thank you so much for taking time out of your evening to join us here on Social Flight Live. I hope you'll come back, and especially as the program moves ahead, when the first flight happens, et cetera, and tell us more, because I know we have just barely scratched the surface of what the challenges but also opportunities are in supersonic flight. I just want to thank you, and as you mentioned, all the amazing people working at NASA's Ames Research Center and Lockheed to make this happen.
You bet. Yeah, I'd be glad to come back again and fill you in and give you an update.
Absolutely. Thanks again. I hope you have a wonderful evening.
Thanks. You too, Jeff.
And to all of you, thank you so much for taking time out of your evening to join us here on Social Flight Live. It is just, it's so wonderful to get to see such cool things that are happening around there and following a program that's going to affect all of our lives, such as NASA's X59 program, is, I just find absolutely fascinating. Please join us again next week on Tuesday, October 4th, when Top Gun Maverick stunt pilot and aerial coordinator Kevin LaRosa will be here on the program talking about the making of that amazing film, what goes into it, what it's like to work with Tom Cruise, and so many more things. And then also on Tuesday, October 11th, Doug Evnick will be here of Tannis Aircraft, and we're going to talk all about how to keep those engines warm and preheated before you fly as the temperatures begin to plummet in the northern climates. So be sure to tune in on all of that. You can find all those programs on socialflight.com. Again, thank you so much for taking time out of your evening, and I wish you all blue skies.